Okay, so I think we can probably slowly start again, and maybe just start with a few reminders, and in the meantime, people that are still enjoying their coffee break will join us. Let me just start by recalling the point where we stopped yesterday. So yesterday we argued that in order to do better than the elastic approximation we were employing at the beginning of the lectures, it's a good idea to promote this iconal exponential to this iconal phase to an operator, and in fact we introduced this this S-ike, which is well, one flavor of it is this one, in which we introduce this sort of W tilde A dagger plus complex conjugate, or well, minus in this case. And here W is really the Weinberg soft factor projected on the physical polarization. So sum over the 4 hard states that take part in our process. And possibly contracted with polarization, let me say, with the TT projection. And another slightly different version of this iconal is instead this iconal operator is this iconal operator sort of including static modes, which instead of having the real part of delta, it includes just the conservative part of the real part of delta, so it excludes the radiation reaction that we saw yesterday, though the structure is very similar. Here, let me call it F, perhaps. And here, the difference is that this F is instead TT projection, including this I epsilon prescription. So if you want in the first one, the 0 omega equal to 0 pole is approached with a principal value prescription. Instead, here it's approached with an I epsilon prescription, which, as we saw, is suggested at least by the Feynman rules. And the difference, well, one difference you can immediately spot is that while this guy is manifestly real, this guy can also have an imaginary part. So as we will see, this will play a role in the angular momentum in a second. And then yesterday we stopped after rederiving the memory waveform, so which we obtained by inserting the canonical graviton operator. So schematically, this guy, this integral over k for me is always the integral over the phase space of the gravitons over the future null cone. And so inserting this operator in the out state produced by the action of the iconal operator on the in state, we arrived at the following prediction for the metric fluctuation. This is just a reminder, right? And 4G over R, and then the TT projection of sum over A, PA mu, PA nu, TT divided by PA dot N. These are just some signs. And then these theta functions, right? Theta A U being the retarded time, which means that the future, in the far future, only the out states matter, and in the far past, only the in states matter. And then we notice that if we approximate this to leading order in G, so we can neglect the distinction between the in and the out particles, because the out particles just differ from the in by the fact that their momenta is deflected by some order G contribution. This can be also written as the sum over the in, and this is just the static field produced by the incoming particles regarded as, let's say, moving Schwarzschild black holes, which do not interact with each other because they are in the far past, plus order G corrections, right? And then yesterday during the discussion session, we started to anticipate this point, which I wanted to present a bit better today before moving on to different topics, which is the fact that these kind of static contributions can be reabsorbed by performing a BMS supertranslation. So as Simone reviewed yesterday during the discussion, the formula for the transformation of the shear under a BMS supertranslation is the following. So BMS supertranslation dictated by this function T of the angles is such that shear transforms as follows: T du CAB. This would be the sort of homogeneous part, which you might have guessed just by the fact that C depends on U, and therefore it's, well, it's Taylor expansion around U going to U plus T gives this term, of course. And then there is an inhomogeneous piece, dAdB T minus gamma, gamma being the metric on the sphere. For me, I think perhaps Simone was calling it Q. And the relation between this CAB and this HAB is that, as you know, the metric fluctuation projected in the AB components would scale like RCAB, right? So it's exactly this guy, except for a factor of R that you can fix by matching conventions. So I wanted to review the fact that there is an expression, an explicit expression for this function T that allows us to dial up and down this static contribution to the H, to the TT part of the metric fluctuation, which is this one. Yeah. So in fact, let me at least sketch this exercise and let you maybe fill in the details later on. So the idea is that we have to regard this as a function of the angles, and in particular we will be interested in this static piece. The reason is that, as you can see, this T already has a factor of G in front, so we only care about this piece, which D acts on T and therefore is linear in G, whereas this piece would have a time derivative, which would kill this piece and introduce another factor of G, and in addition would have a factor of G here. So for the moment we can stick with this one if we don't want to look at the static piece. So let's start. So suppose we start by taking D. Sorry, could you repeat that? For the moment I just pulled it out of a hat, and now I'm going to show that if you apply this transformation, you should get exactly what you have here. This is the objective of the exercise. I mean, this is what this is in this paper of Strominger Givoid of 2014. So I wanted to review it. Well, it is the function that gives this structure. In principle, you can perform supertranslations with other functions. In particular, I wanted to show that this specific combination appearing in the memory, if you want, is the one that corresponds to this special supertranslation. Yeah. So let's see if I manage to get there. So if you want to take D of T, okay, let me focus on one of the two. Let's say that I call it P, right? I would get 2G and then PA dot dBn log. So let me not put the label A just for simplicity, and then I will get plus. Suppose I leave the first term as it is, and then I should act on the log. So the derivative of the log is 1 divided by the argument, which cancels this guy, times the derivative of the argument. So PA dot dA n. And by the way, here the dA will kill, since n is 1 n. So it of course will kill the first component. So these are all spatial contractions when the dA is acting. And then when I act with the second one, 2G, here I could act twice on this guy, right? And then also here, I could act on the log again. So p dot d bn, p dot dan divided by the argument of the log. And finally here, I can only act on this guy twice. And probably should close the round bracket. And now you see, actually the only interesting term is this one, and the reason is that there is a nice identity, which you can show as an exercise, that DADB or n hat more properly, because as I said, the d's kill this one, is equal to minus the trace. So the metric, and since eventually we are going to take the this trace-free combination, all these terms with the gamma simply drop out, right? So I can relate them for all practical purposes because they will drop out from delta T CAB. The only interesting term is this one. So what we get is that delta T CAB is the trace-free projection of this term here. I think also Simona was denoted with some angular brackets, so let me borrow the same notation. But now, of course, what are these dA and dBn? These are the reference vectors on the sphere, right? So we recognize this as precisely another way of writing exactly the same thing that we have here, the TT projection on the sphere of this combination PAPB divided by P dot n. So this sort of completes the exercise. And I mean, conceptually, this means that the TT part of the shear is sort of ill-defined up to this transformation, which in particular, by choosing this specific form, allows us to go from these two cuts or reference frames, depending on your taste. One is the one that we obtained by trusting the Eichhorn operator with these I epsilons, which landed us in the choice of super translation frame in which the shear in the far past is fixed in terms of the incoming particles, and the one in the far past is dictated by the outgoing particles. But nothing prevents us, so this would be the shear, and nothing prevents us from performing another super translation that sets the shear to 0 in the far past and sets the shear at infinity to be the out minus the in. So these two choices differ precisely by the action of this super translation. And in fact, managing my time wisely, I should manage to get to a point in which I will show you instead how also this part. So for the moment, we only had to deal with this part of the super translation, which, as you can see, is a time-independent contribution. So, but suppose we were interested only in the time dependence of the waveform. After all, experimentally, you could say you just wait, and your signal is 0 for some time, or could be -3 for some time. You don't really know, so you just set your detector to measure 0 while you wait for a gravitational wave to arrive. Then maybe you only care about the time-dependent part of your gravitational wave signal, but actually also that one, in principle, can be affected by the super translation, although only at higher orders in G. Very good. So, having said that, maybe let me move some other applications of this formula, which required us some thinking yesterday, so we better use it to do something before moving on. So one additional application beyond the soft waveform is again the soft spectrum, which I briefly mentioned yesterday, but let me introduce it more properly. Are there any questions? Sorry. So the idea is to insert another operator. Instead of inserting the gravitational field operator, now we can insert, for instance, the total energy momentum of the field. You can do it either in a specific gauge or by summing over physical polarization. It doesn't really matter here because we projected this W tilde or F on the physical polarizations on the TT. So okay, let me do it in some gauge. This would be the Donder gauge expression. So this is the operator that you insert, and by now we are very well trained in recognizing what happens when you insert this operator in the sandwich out, P out. A dagger will bring down the coefficient of A, and vice versa in the exponential, so we simply get this expression. And by the way, now for this operator, you can also check it. It doesn't matter if you choose the first or the second type of icon operator for a reason that I will explain in a second. So you can rewrite this as f star kf, where f mu nu is the guy without any TT projection. Well, here I'm using the same convention we introduced yesterday, right? This guy would have two indices, and we replace them by this contraction with the eta mu rho, eta nu sigma, blah blah blah. Here it doesn't play any role, and the same would happen if you had instead neglected this I epsilon. But the reason why it doesn't matter is that we can do a simple power counting. So the I epsilon prescription only matters if you are sensitive to k going to 0 effects, right? So from the measure in 4 minus 2 epsilon, but actually let me do it in 4 since it doesn't give a difference. This is the measure, right? And each of these guys goes like 1 over k. So let me, literally write 1 over k. It would be 1 over omega, right? And then we have another k from here. So as you can see, as an overall, this k is like order k. So it doesn't really matter what happens for k small. This just vanishes. Whether or not you put this I epsilon is completely irrelevant. Okay, and then this is exactly the calculation that we already did yesterday, right? Yesterday at some point we were discussing this 3-particle cut. And if you look back at your notes, what we ended up calculating was precisely the contraction of this structure with this the Donder structure, with this the Donder index combination and k alpha. And we obtained the result, so let me not redo it today. This was just to justify, again, why this was the correct calculation. And then, since we were focusing on the soft approximation, we introduced a cutoff and took the derivative with respect to this cutoff. So the result was 8 pi g. So for this so-called zero frequency limit of the energy emission spectrum. Eight pi g, sum over all the particles, sigma AB squared minus 1/2, and then the integral over the angles, which I left to you as an exercise. And the result was 2g over pi, the sum. Where the sigma b's are just Lorentz products between the PA and PB over which we are summing. Arc cosh sigma b divided by square root. Okay, I wanted to rewrite this formula because now we are ready to reap some of the bounties of having used the soft theorem, which have to do with the fact that this formula doesn't really rely on the small deflection approximation, right? Most of the things that we said yesterday were really tied to the fact that we were expanding order by order in the amplitudes, so order g, order g squared, etc. But the benefit of having used this formula is that this formula is very general. It doesn't require, say, P4 to be a small deflection of P1 and similar for P3, P2. So what we can do now is we can really study this expression, at least for this very simple observable, for generic G in a sense. Or in other words, this formula has a resummed dependence on the deflection Q, right? So it's very instructive to do so for the following reason. Suppose you now are interested in going back to the problem we discussed yesterday at some point, which is, does the massless limit or the high energy limit of the massive 2-to-2 scattering smoothly transition to the small deflection limit of the massless process, right? You expect that since you're considering a higher regime energy in which the energy is very large compared to the masses, the two should be smoothly connected. So here there is something interesting happening in that respect. So suppose you first take the small deflection approximation. So Q much small. So Q is always okay. This is, or when you consider just an elastic process dressed by these soft gravitons, this is the identity we have. And suppose you directly go in the regime in which this is much smaller than the masses. Okay, so this would be the standard post-Minkowskian regime we had yesterday. Then, as I think I also wrote yesterday on the blackboard, we had this d over d sigma, sorry, d omega, zero frequency limit of the spectrum. You can approximate it to leading order as g over pi, q1 pm squared, calligraphic I of sigma, which was a function that at some point, I think you have it in your notes, at some point it had an arc cosh of sigma. Now, if you want to take now the limit in which the energy is very large, so sigma goes to infinity, now we have a problem that if you, for instance, you can do it as an exercise, if you try to compare this to the initial amount of energy, so the total energy emitted in this zero frequency beam to the total amount of energy that the system initially has, so just the P1 plus P2 squared under square root, you will find that this ratio diverges because of this log of sigma that you get from here. So let's say d over d omega ZFL times delta omega, which you can take as order 1 over b, right? Divided by E scales like, well, I guess theta cube in this case, times log of sigma, which is completely nonsensical, right? Because in the high energy limit, so sigma tends to infinity, sorry, we are allowed to stay in the, I mean, take the impact parameter very big in such a way that G over B stays fixed and small. But this log of sigma is completely arbitrary, right? So this means that the formula would seem to predict that the energy emitted by the system is infinite, or can be in general case much larger than the system, than what the system initially had. So this is completely nonsensical. And now let's try to see what happens if we do the opposite, right? If we first go in the regime in which the masses are much smaller than the energy, and then for in particular of this Q, then in this regime you find the following formula, which was in fact obtained in papers by Addazzi, Bianchi, and Veneziano. So you still get this for pi over g, sorry, for g over pi, and then s log of s divided by s minus q squared minus or plus q squared log of s minus q squared. So now you see that, okay, s would be e squared, so just minus p1 plus p2 squared, the Mandelstam invariant s. So you see here dependence on q is really resound. It's a non-trivial function of q and s. And already this one is, although I didn't really write it down very explicitly, there is still this sum, but if you write it down explicitly, you will see that it's also a non-trivial function of q. And then now what we can do is take the small deflection limit. So now if we take theta small, we learn what the actual behavior in the ultrarelativistic limit is. Right, this is a version of the ultrarelativistic limit because the mass is very small. And you get gs theta squared divided by pi log of 4e theta squared. So you see the problem is that the energy, so the log that here would have been a log of sigma, instead in the actually correct answer, which is not infinite, is a log of theta, and theta is of order g, right? Theta is this roughly this g over b. So in a sense, the general lesson to be drawn from here is that taking the ultrarelativistic limit, the naive ultrarelativistic limit of the massive result seems to be correct as long as you don't have logs around. And the reason is that this expression here, regarded as a function of q, in the presence of log, starts developing a branch cut. And of course, the Taylor series stops converging when you, at least naively, unless you do some redefinitions of variables, you encounter the branch cut, and the Taylor series simply stops converging in terms of q. So in a sense, this is the limitation to the validity of the PM approximation that I was mentioning, perhaps in the first blackboard or two. So it is in this sense that for some observable, the velocity sigma that you can take, so the gamma factor sigma that you can take for order by order in the PM expansion is very large, but it's not arbitrary. It is limited by the point where you encounter that branch cut, And this leads to a bound in the validity of the PM approximation, which roughly you can see by looking at that formula expanded out explicitly, means that sigma must be smaller or equal to 1 over theta squared. So it is in this sense that for small deflections, velocities can be parametrically large, right? Because theta is small, so this is very large, but not arbitrarily large, at least not for all observables. For some others, it seems that we are luckier, right? For instance, yesterday we were discussing the deflection angle at 3 p.m. At that order, there was no log in the massless answer, so it just happened that we could take the PM, the fixed PM expression and send sigma to infinity, finding the right result. It turns out that you have a log, you're out of luck. Okay, so this was the first sort of comment I wanted to make on this result we saw yesterday, and now we are in a position to, maybe let me keep this black bar for now. We are in a position to apply this machinery to a slightly more subtle observable, which is the angular momentum. The logic will be principle very similar, but as you will see, that there is a bit of a difference in the following. So now the operator that we want to insert is no longer this P, but is really J. So J alpha beta, which again, let me use the Donder gauge. This double arrow means that it's 1/2 the derivative acting on the right minus 1/2 the derivative acting on the left. Oops. Times A. Okay, so what happens now if when you try to pull down, when you try to insert this in the sandwich given by this out state and apply contractions with this Eikonel operator, then you will find that there is a stark difference whether you use this one or this one. So if you use this version of the Eikonel operator, which does not include the static mode, you will simply find 0. So very easy exercise that I leave for you. And instead, if you use this one, you have to deal with several subtleties, and the result is non-zero. So the first subtlety is the following: that usually when we were able to, okay, let me write down the result. Let me call JTT this sandwich. And what happens is simply that A pulls down a Dagger coefficient, blah, 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 exactly as I said all the time. So there is an integral over the phase space of the gravitons, and in principle there is still this cutoff, although we will see that there is a surprise also there. So integral over K, 1/2. To be completely explicit, let me make this 1/2, and then the left-right arrow completely explicit. And then the sort of spin term. This is not, yeah, this 2 here is because the graviton has spin 2, of course. Mu alpha star, mu beta. Okay. So 2 comments. The first one is that you immediately see why in the massless, in the first case you were finding 0. Suppose you were to replace this F by this W, well then the W is manifestly real, so this is clearly an imaginary part, and this gives 0. Instead, with the I epsilon, it's non-trivial. The second point, which maybe I will come back to later when we discuss the radiative contribution, so beyond the soft limit, but for the moment, let me give it to you as a statement. Usually, in these kind of games, we were able to replace, for instance, over there, right? We were able to replace this sum over physical polarization that is involved, appears due to the TT projection with the contraction just with eta mu rho, eta mu sigma, blah, blah, blah. And the reason was that our amplitude satisfied the identity, this sort of word identity, right? Now, it just so happens that for this F mu nu, this is no longer true. precisely due to this zero frequency static mode. So suppose you want to calculate n mu f mu nu of k. Now you have a bit of a song and dance to do in order to take care of this I epsilon prescription, and you can show that the result is I pi kappa, or square root of 8 pi g. By the way, square root of 8 pi g. And also here. Times delta of omega, the sum over, say, the in state of PA nu. So it's no longer true as an algebraic identity that the contraction with k mu is 0. I mean, the contraction with k mu will still be 0 because n and k differ by a power of omega. So omega times delta of omega would be still 0 as a distribution, but that's not what we want, right? We want to make sure that whenever we contract this guy with k or with n, which appears in the expression for the TT projection, right? Which you have also in your notes from yesterday, we get 0 as an algebraic identity. And the reason why this is important here and was not important over there is again the power counting. So the power counting is very, very easily deduced from the other one. It's exactly the same. The f go like 1 over omega. It's just that now instead of inserting k alpha, we are inserting k alpha ddk beta, which does not scale with omega, right? Because there is an omega upstairs and an omega downstairs. So the power counting is d for k, delta of k squared, 1 over k, 1 over k. So in this case, if you have a delta of omega somewhere, you can get a contribution. And this is indeed the case. So in fact, as we will see in a second, the whole contribution that we get is precisely due to this delta of omega. So from the static contribution, from the static component. However, let me not take this epsilon to 0 just yet in order to isolate this delta of omega. Let me keep the expression generic as I wrote it over there. Then we will do the calculation, which is very similar to this sketch, the calculation, which is very similar to the one on the spectrum that we had yesterday, and then discuss it. Any questions? Yeah. Y0 in which part? Yeah. So let me see. So this guy is the complex conjugate of this guy, right? So, and there is a minus sign. So basically, this is the imaginary part of this thing. But in the case without the I epsilons, this W is real. So we have to replace F with W, and W doesn't have any, so it's a principal value of 1 over omega if you want. There is no I. So this is 0 because it's the imaginary part of something manifestly real. I mean, you can go through the calculation and make sure, but this is in practice what is happening. And the spin component is the same because the mu's are contracting and there is an anti-symmetrization. So you can also write it as this minus the one which replace beta with alpha, which is also the star of the one that with alpha and beta. So exactly. Okay, so let me, yeah, as I said, here the calculation is a bit longer. So the bottom line is that now we can no longer simply replace small f, which is the TT. So essentially small f is the TT projection of this capital F, as you remember in the notation we had. Well, it's still over there, yeah. They are exactly the same except for the T projection. Now, due to this, we can no longer replace capital F with the small f, so, but let me separate the two problems and discuss them one at a time. We can still, so what is true instead, and okay, it requires a calculation that maybe I have time to do, is that if F satisfied this, so for instance, if you add the other one, so if satisfied this with this equal to 0, then you would be able to, although it's relatively non-trivial, right? Because now there are derivatives that act on this projector. So could worry that maybe even if this word identity is satisfied, then maybe you cannot replace the CT projector with our beloved eta rho alpha, eta mu rho, eta nu alpha, etc. But this is the case, in fact. So let me write down an equation. Maybe it's easier than the training word. This TT projective thing, you can write it as something, which I will write down in a second, plus terms involving n mu f mu nu, which is non-zero in this case. But first, let me focus on this guy, which has a nice form. So here appears our beloved reference vector independent, manifestly covariant structure. And here F is capital F, so the one without the TT projection. Sorry, F rho sigma probably. And then, okay, let me actually make use of this double error notation just to avoid having to go in the next line. Plus 2 F star mu alpha beta mu. So this is actually easy to calculate. The reason is that now F has the structure that we also use to calculate the spectrum. The only difference is that you have some more tensor structure to deal with when you perform the K integral. But this is very, very similar to the one that we did yesterday. In particular, the angular integral. So the strategy is, again, you separate out the K integral into a frequency integral and an angular integral, right? The angular integral is exactly the same that we had in the spectrum. It will give this Arcosh. The novelty is due to the omega integral, which now is non-zero precisely to this I epsilon prescription. And in fact, let me give you the relevant building blocks in case you want to reproduce the calculation. The omega integral, you will need to use the following. So you can show that you can use this, the structure of this expression to recast this integral, which would be from 0 to omega star in the frequency, as an integral from minus omega star to plus omega star, which is always a bit easier to evaluate. And then you have omega d omega, for instance. And let me even be more explicit. Let me turn the I0 prescription into some small parameter, and then I'm sending to 0 just to be a bit clearer. So let me call it lowercase lambda. So you have a capital an omega star, sorry, and a small lambda, which is like the I epsilon prescription. And then eventually we are taking the I epsilon prescription to 0, the epsilon to 0, or the lambda to 0. And this is minus I pi over 2 eta n minus eta m. Or in other words, if the states are both incoming or both outgoing, you don't get anything, you only get something if one of them is outgoing and one of them is incoming, so that you get a +2 or a -2 here. And the nice, well, the perhaps slightly surprising feature, if you hadn't thought about this zero frequency problem a few minutes ago, is that, as you can see now, the dependence on omega star has dropped out. You can actually check this. It's a very easy. It's a very easy integral to do. So no omega star dependence. And this means that we can also send omega star to 0 at the end of this calculation. And we still find a non-zero result, which is the one I'm going to write down next, perhaps over there now. So if we put together the integral over the angles that we discussed yesterday with this integral over the frequency and turn the crank, the result is the following. J alpha beta, which is not the JTT, which I'll come back to in a second, but it's still interesting for a reason that I will say in a few minutes. You can write it again as a sum over A and B, pretty similar to the one for the spectrum, but let me give a name to these coefficients because they're a bit longer. And then it has a tensor structure which only depends on the PA-PB, of course. And these C's, when you say C of sigma or C of some variable, of course you have to substitute PA.PB as its argument. 3/2 minus 1/2 and sigma arc cosh sigma divided by square root of sigma squared minus 1 plus There we go. Okay, so now we could worry that we didn't do really anything yet because we still have to add this guy to that other guy, right? Terms involving n dot f, which in this case are not 0. Okay, another property that unfortunately I don't have the time to show you is the fact that now a simplification happens if you focus on a process in which you define the splitting between the ij and the j0 components in the center of mass frame. So center of mass frame, the one that we also introduced yesterday at some point. So it's the one in which the spatial momentum vanishes initially, and since we are focusing here on the zero frequency approximation, it also vanishes finally because no energy is emitted, right, as an integral. There is only a zero frequency contribution that goes to 0 if you take omega star to 0. In this frame, what happens is that j ij tt is actually equal to j alpha beta, sorry, to j ij. So to specify the logic, specifying the center of mass frame fixes for you the Lorentz invariance, I mean Lorentz freedom, so freedom to perform boosts, so it fixes a splitting between time and space. And what we usually call the angular momentum with capital A and capital M is the spatial components of this tensor, J alpha beta, in the center of mass frame, which is sort of the natural one to sit in for the binary. In this frame, there is no distinction. So what we got here is actually the full contribution of the static modes to the spatial angular momentum. Spatial angular momentum. Instead, the subtlety, so with these terms involving n dot f, appears for the 0i components. So you can show, in fact, that the 0i components are different. So 0i tt, or I0 tt, I've written down. It's always very easy to get confused with the signs here because everything is antisymmetric. So it has another contribution. If you actually evaluate it, it's actually a bit easier than the one needed to calculate this guy because you can use this expression, which is, after all, very simple. To GE sum over the same functions C that appear here, but now evaluated at a different argument, times PAE. And this C sigma A is the gamma factor of each particle as seen from the center of mass frame. So EA divided by MA. So it would be the Lorentz factor as defined in the CM frame. So you see they're a bit different, but the difference is only important for these 0i components, which sometimes are called the mass dipole or mass dipole moment. And from a, let's say, symmetry point of view, the angular momentum is, as you know, a manifestation of the invariance of the theory under rotations. So they are, if you want, associated to P dot B or B dot P, the spatial one. And instead, this mass dipole is associated to the invariance under boost, again, as defined in the center of mass frame, and is instead related to EPI minus XI, X0 pi minus Xi, the energy. So if you want to the position of the center of mass as to the subtraction between the freely moving position of the motion of the center of mass and its initial one. So if you want the initial position of the center of mass, which if the system wasn't radiating wouldn't change, right? If you put it in the origin, sitting still at the beginning, it would stay there, but instead if the system radiates, it would start moving. But as you can see, it's a bit of a subtler quantity. And now maybe let's try to give an intuitive explanation as to why this term only matters for these 0i components. I mean, you can do the calculation, but is there a sort of way in which you could have guessed it? Well, it has to do with the fact that in the center of mass frame, by definition, this thing here, so P1 plus P2, it takes a very simple form, right? It's 0 in the, so the spatial components are 0, and instead the only non-zero component is the time like one. So this is why the splitting is particularly nice in this, precisely in this reference frame. Of course, you can do the calculation in a generic frame, and then you will find that there are differences in both between the TT and the non-TT version of this angular momentum. Physically, what you're doing when you project out these longitudinal components from S mu is that you are projecting away the Coulombic field, right, the longitudinal modes of the Coulombic field. So in a sense, I would say that you can think of them as both interesting quantities. This would be the energy momentum tensor, the angular momentum tensor of the gravitational field, in which one includes the Coulombic field in the definition, and the other one would be the one in which it excludes the Coulombic longitudinal field. And in fact, I mean, again, I have really no time to go in this any detail, but you can check that you can repeat the exercise we just did for the energy emission spectrum to study the large energy limit, right? First take the small deflection limit and then the high energy limit, or vice versa. First take the high energy limit and then the small deflection limit, and you will find that this guy behaves exactly like the spectrum. So maybe let me add it here as a list of our conclusions. This is a nice ultra-relativistic limit. Of course, before expanding it in PM, so you can take first the ultra-relativistic limit and then the small deflection limit, and then you will find that there is this theta log theta contribution. And then here instead, the guy that has a nice UR limit is this one. But this one doesn't. So apparently it's important to subtract the Coulombic field in order to take the ultra-relativistic limit. Otherwise you get an ambiguity in this case, like the logarithm of the two masses of the two binaries, of the two objects comprising the binary, which is arbitrary, right? I mean, you take the mass to 0. Okay. So maybe since I'm not doing so bad on time as I had anticipated, let me try to sketch at least why. Let me try to do at least one calculation, otherwise I feel like I'm cheating. Let me try to sketch why why for an object satisfying the word identity you can indeed replace the structure with the small f with the one with the capital F. So you can remove the TT projection. Maybe to do that, in order to save still a bit of time and still have some time to discuss what happens beyond the zero frequency limit, let me focus on a slightly simpler case, which is the one of a spin 1. So suppose we have now, I mean, the waveform is just one index. This is the TT projected guy. So the T projected guy. In this case, there is only one index, right? So P is lambda squared is equal to 0, k squared is equal to 0 because it's on shell, and lambda dot k is equal to -1. So this is really the transverse projector. Whereas instead, of course, for our gravitational case, we would need the transverse traceless projector, but okay, for today, let me focus on this simpler object. In addition, let me define, and F now satisfies the word identity. Exactly, so let me emphasize, n mu is equal to 0, and k is equal to omega n as usual. Okay, then let me also introduce this short time notation just to be a bit quicker in writing the next equation. So k alpha dk beta. So you can repeat all that we said for the gravitation and for the electromagnetic field. You can even guess the formula just by looking at the result and removing some of the indices. And the bottom line is that you find that Jt, the transverse guy, would be minus I the integral over k f star mu d alpha beta f mu, plus here there is no 2, there is 1, right? Because the spin of the photon, or the helicity of the photon is 1. Okay. So let's see what happens when we start substituting this combination. So d alpha beta f mu, d alpha beta, the projector, right? So let me write it down explicitly. Times capital F nu. Okay, now of course in this term there is no problem. You can just act it through the eta because it's a constant here. Here instead it's a bit trickier, right? Because in principle you could act on several things. Both D and K depend on K. K obviously because it's K, and lambda because of this constraint, right? So lambda, for instance, one choice of lambda could be something like 1 over 2 omega K0 minus K or something like this to be checked. And please check the overall sign. But just to say, it depends on K. But what happens if you, we have to remember that this guy eventually is contracted with this one, which is still transverse. So suppose we act on K, let's see what happens. So if we have lambda mu, it is not a specific problem, you get d alpha beta k mu f mu plus d alpha beta lambda mu k nu f mu plus lambda mu k nu d alpha beta f mu, and then you have to go on with the other guy, which, okay, just nu and mu interchanged. So here I'm letting it act on lambda, I guess. Okay, mu f mu plus, that's it, right? Plus, okay, lambda nu k mu d alpha beta f mu. So there are for sure some terms that will vanish when we contract this back with f star mu, right? For instance, say f star mu contracted with this guy is going to be 0, right? Because f mu contracts k mu, and this is 0. So we can neglect this guy. Similarly, we have to be careful when we contract k with f, because that's also 0. And let me see if there are other simplifications. So this guy will give something like k alpha delta mu beta. So this guy we have to keep. Let's see, maybe help me out if you spot something else. This guy is probably there to stay, right? Because lambda can contract our friend. And k nu probably, did I make a mistake in the contractions of nu? Yeah, anyway, as you can see, I didn't rehearse this calculation, which is a bit dangerous. But anyway, this is a bit the idea. You have to substitute this through and check that several of these terms cancel out. And you will find a non-trivial cancellation between the spin term and the transverse traceless term. So maybe in view of the fact that I would probably spend a lot of time in this calculation, let me move to the non-zero frequency part. But at least the logic is clear, I hope, right? Okay. So now the logic is, up to now we have used this zero frequency, or this small frequency limit in order to simplify our life a little bit. But in principle, we want to come up with predictions for the gravitational field also beyond the zero frequency limit, right? So in that regime, we can no longer rely on the Weinberg approximation, but we can still try to do something. So the objective for this last half an hour or so is to illustrate that something. So the idea is to, as I was also sketching mentioning the other days, there are two possible types of approaches to our problem. One is to try to first find a good approximation for the S matrix, which comes in the form of our iconal. And up to now, we approximated it as I real part of 2 delta, integral of the soft factor. And well, the first guess that you could come up with is, instead of putting the soft factor here, let's try to put something that is probably, hopefully should hold also beyond the soft limit. So let me denote it with this capital A, and probably add an I here in front. I of k. And now the issue would be that, well, the guess, it would be that this guy is the waveform beyond the static limit, right? Or the soft limit. Here, let me focus on, again, instead on the version of the iconal operator, which doesn't have any zero frequency mode for the moment, just because it's a bit simpler. So beyond the soft limit. And why is this? Well, of course, because then if we use this to again calculate our expectation value of h mu nu, everything we did yesterday will go through, except that now we have this sort of new ingredient in the exponent. So this will lead to a prediction for h mu nu, which is 4g, or asymptotically as r goes to infinity, omega and, sorry, u and n fixed. It's 4g over r, the integral from 0 to infinity, the omega, 2 pi e to the minus I omega u. And now the difference is that you have this w divided by 8, square root of 8 pi g, right? Because you remember in the step we took yesterday, at some point that square root of 8 pi g sitting in front had disappeared, so this is the right rule to remember, plus complex conjugate. So this is option 1. And of course, now the way in which you fix w is exactly the same way in which we had fixed delta 0 and delta 1 in the first lecture. You try to match to the amplitude and see what the exponentiation, you check that the exponentiation holds order by order in the loop expansion. So in this sense, this is not a proof. This is a working hypothesis that you can then check order by order in perturbation theory. So order by order in G, you can do two things. Check, let's say, star, as we did for e to the 2I delta. And deduce the new pieces, the G expansion of W, again, as we did for delta, right? You remember yesterday, we started out by finding delta 0 from the 3-level amplitude. Then in the one loop amplitude, we checked that there was a piece canceling out against delta 0 squared divided by 2 factorial, and we deduced delta 1, and the procedure goes on. And so deduce also W0, W1, and in principle higher order. So this will be the 3-level waveform, this will be the one loop level waveform, etc., etc. Another option, which I think I mentioned several times also answering questions, which eventually is completely equivalent, but it's as always interesting to check whether one or the other agree. So is to start out with an outstate dictated not just by this classical approximation of the S matrix, which is this iconalized S matrix, but really by the full S matrix. And directly use it to calculate some observables. So for instance, if you're interested in the waveform, you would now insert, again, this h mu nu in the out state. Or you could insert the momentum of particle 1 if you wanted to reproduce the calculation of the impulse that we calculated from the iconal yesterday. And in principle, you can consider also other stuff. You can insert the two operators that we just discussed, the angular momentum and the energy momentum. So maybe in the remaining time, what I wanted to do was to present the structure of this W in terms of amplitudes at leading and subleading order, which is something that we didn't do yesterday, and maybe compare it with what happens in this KMOC story. Are there any questions on the logic here? Okay. So maybe let me start by revisiting the calculation that we did yesterday. So the impulse from the yep. Yes. what is this dot dot, exactly. So the idea is that here I should put all the things that scale classically. So for instance, you remember delta was scaling like gm squared over h bar, and then it had the log b piece plus gm over b plus higher order corrections in this limit. Here is the same for w. There is a piece that if you look at now, instead of the 2 to 2 amplitude, if you look at this 2 to 3 amplitude, there will be a piece that scales that is leading at each order in the loop expansion in this parameter here. And then order by order, you will either find iterations of that or pieces that are subleading. But in principle, you could also find things that are suppressed by this parameter. So for instance, here there would be things that scale like h bar over gm, say to the 0, to the 1, etc., right? So of course, multiplied by appropriate powers of the other parameter in order to make it of the right order in G. But in a sense, schematically, things that have dependence on h bar, which is in the numerator, not in the denominator, right? So they are small in the classical limit, or at least order 1 in the classical limit, which is small h bar. Right. Exactly. Or, well, there is an h bar which is actually in the denominator, so they are very big. That's right, that's right. And then they don't receive any h bar correction, so this is really the classical expansion of the exactly. That's right. Exactly. So of course, as I said, this is an educated guess, and there are several reasons. One of them is that in the classical limit, you expect that there is no correlation among the graviton emissions, and therefore you can just approximate them as we did for the Weinberg case in the soft limit. The difference, the conceptual difference, is that in one case you can do it even in the quantum sense because they are always very soft, completely uncorrelated. Here, the educated guess is reasonable because we only want to do it in the classical limit, even if the gravitons are non-soft. But for the moment, this is just a conjecture that is being checked at higher and higher orders as time goes on, but I wouldn't say it's on the same conceptual footing as the Weinberg one. Yeah, exactly. For instance, one could wonder, what if you start adding something, this A-DAG array? Does that coefficient scale as 1 over h bar, or is it further suppressed? So it doesn't mean much putting it in the numerator. You might well, so in the exponent, you might as well just put it in from the prefactor. For the moment, there is no evidence that you should put any A-DAG array, so correlator. But okay, this is a bit up for debate at the moment. Asking different people can lead to different answers at the moment. I would tend to think that this is correct in the classical limit. But okay. One way to check this would be, for instance, to check double emissions. So this 3-level amplitude, for the double emission, it has been shown that it's further suppressed by h bar, so that there is no correlation. But I guess the first non-trivial check would be to study the one loop correction to that and see if it factorizes at the product of two of these guys. And it's 0 up to quantum corrections. This is a non-trivial check, but would shed light precisely on the question that you're asking, right? Because just because the correlation would be the double insertion, expectation value minus single insertion, which is the correlator. Okay, so let's see. The idea is to now switch a bit gears and compare the iconal and this KMOC. So let me start from the impulse. In the iconal, we had 1 plus IA0 plus A1. Let me stick to one loop because I will discuss the waveform only up to one loop. And then yesterday we said, due to a stationary phase approximation in the inverse Fourier transform, you simply deduce that Q1 PM, say, is the derivative of this delta 0, which had this expression, right, minus 4G M1 and 2 divided by B times sigma squared over square root of sigma squared minus 1, which is just a reminder. And Q2PM is the same. Let me not rewrite the expression that you already have in your notes, but it's still just the derivative of this B mu. So to summarize, the prediction from the iconal would be that up to order G cube correction, so this is order G and this is order G squared, you have minus B mu over B, Q1 PM, the absolute value plus Q2 PM. Plus. Okay. Now let's try to compare with what would happen if one would instead stick to this more sort of systematic KMOC observable based approach, then you will need to calculate out P1 out minus in P1 in, which is okay, exercise for you, what these in wave packets do. So these are some integrals over the wave packet of the particle, e to the ib dot b1 dot p1, and similarly for p2. You can show that in the classical limit, when the wave packets are sharply peaked on the classical values of the incoming moment, etc., what this in thing does is to just perform the Fourier transform that we had also in our this tilde here. So here what we get, remember, is so out is 1 plus it. So here we get, let's say, let me start from the one in which out is star one. So here I'm expanding 1 minus IT dagger, so I get a minus IT dagger, and then P1 acting on the in, plus I in P1, T acting on the in, and then I have this extra, the extra term in which both T and T dagger appear, so plus in P1, sorry, T dagger, P1 T in. And let me try to do this very dangerous operation of pulling out an I. So I here, nothing here, and minus I here, I guess. Okay. And then there is this I, yeah, okay, let me keep it like that. Then what happens is that we have to insert complete sets of state in this guy in order to make sense of it. So the diagrammatic interpretation, this is a two-particle state, right? So we can think of this as having 1, 2, and this guy as having 3, 4. And then performing the Fourier transform, as I said. So the diagrammatic representation of this would be the S matrix for the 2, 2, 2, in which I measure the momentum of particle 4, the one in the out state, minus, well, minus P1, because the momentum of particle 1 is actually minus P1, right? The amplitude, but the amplitude starred, right? Because there is this T dagger. And then minus I, this thing, and as I said here, we should insert, let's say, some resolution of the identity, which would involve a 2-particle state, a 3-particle state, and further several particle states. Let me stick to one loop, so we only need the 2-particle state, and then other stuff. And then we have to add, then we have to measure the momentum of particle 1 in this cut. So we have to, let me call it this L minus P1. So this guy is L mu minus P1 mu. And let me go a bit up. So let's try to see what happens at 3 level and at 1 loop for this quantity, right? So this is what I was calling Q in the other part of the blackboard. So Q 1 p.m. is just the Fourier transform I times the Fourier transform of this guy, which is P4. Now the 3 level, for the 3 level, this star doesn't do anything, right? So we can just do P plus P1 times the amplitude. Oops, here I was missing the Fourier transform. Sorry about that. And this is exactly the Q mu, and IQ mu is the derivative with respect to B. And the Fourier transform of the 3-level amplitude is the leading iconal. So up to now we seem to be doing pretty well. This is exactly the same prediction as from the iconal. And let's see what happens at next leading order. And here I have to keep P4. And then what I want to do is to use a bit, unitarity, which, as we saw yesterday, tells us that twice the imaginary parts of the 1-loop amplitude is the gluing of 2 lower loop to 2 amplitude. So we have P4 plus P1, so Q mu, times the real part of this one loop amplitude. And then let's see if I manage to get the sign right, plus I over 2 P4 minus P1 times the imaginary part. So the imaginary part is the cut. And then minus I, I'm just copying from this cut here. I hope it's visible. L minus P1. Right? So let's see if I manage to do the algebra. I have will be P4 minus P1 plus plus 2P1 minus 2L. Right? This is the total of these two. So P1 now plus P2, which is Q, minus twice L mu. And let me remind you that this is L minus P1. So essentially what happens is that the momentum flowing here is L, and the momentum flowing here would be Q minus L, right? Because Q is flowing out from here, and here just L. So the bottom line is that from KMOC we seem to get a slightly different structure, right? That the 2pm impulse is I times the Fourier transform of Q times the real part of this, but the real part of this, its Fourier transform was precisely delta 1, if you look back at your notes. So we seem to get the derivative of delta 1, and then we have this cut. So I guess plus I, the Fourier transform of I over 2 L minus P1 times this cut. So almost correct, right? From there we would have just gotten this term, and then we seem to be getting this other term. Now it turns out that the two are actually equal up to a subtlety, which I think I mentioned very quickly in the first lecture and then never mentioned again, so let me emphasize it again. You remember in our first drawing of our 2-to-2 process, we had this drawing with the incoming momenta and this initial impact parameter, which I called Bj. And then I never emphasize it again, but from the drawing, so let's say this is the incoming and this is the outgoing momentum, from the drawing, it's clear that, at least in the elastic case, the vector, the momentum transfer of the process is not aligned with Bj. It's aligned with this other vertical line, which is symmetric with respect to in and out. So this is what I'm going to call Be. So what turns out is that the two formulas are exactly the same if you interpret B in these formulas as Bj, and therefore, rightly so, Q, when you expand it in terms of P and Bj, has a larger component along Bj and also a smaller component along P. It's just that the two reference systems are not really aligned. I mean, the reference system you're using is not exactly aligned with with your important vector. And the first line and the iconal is instead written down in terms of this Be. So to correct my calculation, this is the right fix. And in fact, you can go through, but you can try to also put together these two exercises and try to use this these observable-based ideas with the iconal operator that we introduced, and you will find that in both cases you always get that Q is aligned with Be as the picture sort of proves, right? Now, in the last few minutes, what would happen if instead you use the waveform? So from here, let me not erase this because this is exactly what I want to calculate now. So to reiterate, here, for the elastic case, the full amplitude had a real, so the three-level amplitude is just the three-level amplitude, it's real, rational, etc. The one loop amplitude has a real and an imaginary part. The real part is related to the iconal, and its derivative gives the subleading correction to the deflection, or to the angle, if you prefer. And the imaginary part appears, but only if you're writing things in this sort of bad reference frame. In the right reference frame, you can just throw it away. In particular, you can throw away these two particle cuts involving the massive particles. Now let me illustrate the structure of the, okay, the 3-level 5-point amplitude is just related to the waveform in the obvious way. Its Fourier transform is literally the waveform at leading order. Again, sort of in analogy to what's happening there. The one loop amplitude is a bit more complicated. It would have a real part plus an imaginary part dictated by the sum over all the cuts, right? We use again the unitarity equation. Now the unitarity equation tells us that twice the imaginary part of the amplitude is the sum over all the possible cuts that you can draw with this initial and final state. So the novelty is that here we have more possible choices. We have the sort of obvious one, then some that are a bit less obvious. For instance, you could first exchange an intermediate to particle state, insert an intermediate to particle state and then have your 2 to 3 amplitude, or you could do the opposite and insert a 2 to 3 state and then never let the graviton interact again. So let me draw it like this. And then also we have new processes which are associated with the fact that you could have an intermediate particle state involving a massive particle and only a graviton, which then needs to re-interact with one of the two particles. So this is the structure of the one loop amplitude. Now what happens when you go from the amplitude to the observable, so to the waveform, which is very much analogous to what just happened here. We were going from the amplitude to the observable, which is the impulse, is that you have to be a bit careful about the structure of the cuts, either because you're matching to the diagonal exponentiation or because you're inserting these KMOC cuts. So let me see. Let me show you how this works. Maybe let me first do the KMOC now and then the iconant, just to vary a little bit. So now we want to, effectively what we want to calculate is out, A, out. And out is equal to 1 plus IT. So here what I can get is minus, sorry, well I could get minus I in T dagger A, but this is 0, right? Because I am assuming that in our in state there is no radiation, so this vanishes. Plus I in A T plus in A dagger T A in. Again, let me pull out a factor of I for simplicity, and maybe also the in, which only insert our Fourier transform after all, T dagger A T. And then let me evaluate it order by order in perturbation theory. So this would be effectively the wave shape after, what happens is that this would be the insertion of H, and then we have to take this asymptotic limit, you remember. What happens in that limit is that you get rid of this I, effectively. So at leading order, remember, these are effectively 3-4 particles, and these are effectively 1-2 particles up to the Fourier transform. This is the 1-2 process, sorry, this the process 1-2 that goes to 3-4 with the addition of a graviton. So it's exactly the 2-3 process. And the 3-level, this is everything we get. So we recover that equation. Now let's see what happens at the next order. This is again the 1-2 that goes to 3-4 plus a graviton, but now at one loop. Minus I. And then you see here we have to insert some intermediate state. And we can start by inserting just the 2 particle state. The other ones would contribute to higher powers of G only. We stay at 2 loops here. So we have a process that goes to, yeah, maybe let me insert it here, just for clarity. Doesn't matter, of course. So here we insert 1-2. So there should be an intermediate process in which 1-2 goes to, well, at least 1-2 must be there, so two massive particles plus a graviton. But this is inserted inside the cut. And then we should go back to another two particle insertion. So the only cut that we have to subtract is precisely this one. This is clear. This is because the A is only inserted inside the cut now. Okay. Okay, so then looking at this equation, we deduce that the full waveform kernel can be written as the real part Then there would be plus I half the sum over all the cuts, but we see that we get a -1 instead in front of this guy. So the final result is that this stays as it was. This changes sign. Maybe let me use a color to emphasize that. There we go. And now, let's say the last piece of information that I wanted to convey is that if you compare, by analogy with what was happening for the 2-to-2 process, here you remember we also had a 2-to-2 particle cut in the KMOC formulation, which was simply there in order to rotate the frame from the bad one to the good one, so from BJP to BE and let's say P tilde. And exactly the same happens here. So these two these two cuts with two particle intermediate states are simply there in order to rotate the expression from the not so nice reference vectors to the good ones. So the bottom line, maybe let me write it down here. The bottom line is that if you use the good reference vector, so BE and, this piece of chalk is terrible. If you use BE and P tilde, so the symmetric reference frame, the one loop waveform kernel, so the thing of which you have to do the Fourier transform. Yeah, sorry, again forgot the Fourier transform. Let me remove the tilde. In order to get the one loop waveform is the real part of the 2-to-3 amplitude plus I half only these cuts here. Okay, so this is somehow the conclusion. Maybe one last thing I wanted to say is, which is somehow in topic with this school, is that one has to be careful about these guys because they are very much infrared sensitive and also have to do with the super translations in a way that I try to convey in a few minutes now. So the first issue is that while this guy here is infrared safe, these two guys have an infrared divergence. And the reason is, well, is the usual one that you can find also in Weinberg. The fact is that each of these guys can involve, in particular, let me pick this one, can involve a sub-process, right? In which the two massive lines exchange a very soft graviton. And this process, as usual, gives rise to an infrared divergence in the integral. So what you can do is that you can write this loop integral explicitly, put a cutoff. This is exactly the same calculation that we did for the 2-to-3, for the 3-particle cut in the maybe second lecture. Put a cutoff, use the soft theorem, use the soft approximation for this 2-to-2 sort of Compton amplitude, right? And what you will find is that to leading order, each of these two cuts has a so let me put the I over 2, because otherwise I find I always forget it if I sometimes don't put it in one intermediate steps. This is M1, M1, omega 1. You remember omega 1 was just P1 dot K divided by M1 times. So the benefit of doing this analysis is that, of course, the infrared divergence appears with the log of its companion scale, which this would be an unspecified scale, but of course the right invariant to be associated to this cut is omega 1 times the amplitude without this, right? So the 2-to-3 amplitude at 3 level. Let me call it like this. And here there is another subtlety, the fact that so here it's really the 2-to-3 amplitude in the in D equals 4 minus 2 epsilon. So in particular, here we are only predicting the infrared divergence, but you should be careful because if you write down the amplitude here will depend on epsilon. This is what I'm trying to say. So this is a problem, apparently, because we have an observable which depends on an infrared divergent piece. However, this problem is sort of easily dealt with in the following way. So let me write this W1 by isolating this, this divergent piece. So let me define some subtracted or regularized contribution. See if I found it in my notes. Yeah, okay, let me add and subtracted this piece essentially. But okay, but the key idea is that you shouldn't write separately W0 and W1. You should write everything. So W0 plus W1. This is the 3-level amplitude plus the real part of this 2 to 2 plus this infrared divergence, which when summing over M1 and M2 will give M1 omega 1 plus M2 omega 2, which, well, there is an identity. You can write this as E omega, the total energy and the frequency in the center of mass frame, times this minus 1 over epsilon, plus a sort of regulated I half. As you can see, I was about to forget that. Let me define it like this, subtracted. So this is the finite part after subtracting this 1 over epsilon. And then you see it's very natural to exponentiate this infrared divergence, again, very much in the spirit of what Weinberg tells us. Order by order in G, of course, because of course the other terms will be higher order, say G to the 7 half. There we go. And then let's go back, let's see if I still have it somewhere. Of course I erased it. Anyway, so the idea is that you remember this guy was appearing in the expression for the waveform with a Fourier transform. Let me erase the part that has to do with the impulse. So you remember H was for G over R. This W, so let me write it down explicitly. Yeah, there is also an I. And then let me define this as W sub. And then you see somehow what this infrared divergence is telling us, and with this I think I can conclude. The fact is that our perturbative approximation doesn't really use the right asymptotic states because we know that in the presence of gravity, the asymptotic states keep interacting, so they're not really asymptotic and free particles, etc. But we can hide our ignorance about the actual behavior of the asymptotic states by redefining U that goes to U minus 1 over epsilon G times E. So this is a sort of renormalization or retarded time. And of course, I mean, this is an infinite subtraction, so the actual meaning of this is that simply we are not able to predict this constant. So in general, we can subtract this or GE times the log of any scale. So we can perform any finite shift or retarded time, or in other words, this means that our amplitude-based calculation, but in fact, something similar had already appeared in papers in the PN calculation, so purely classical by Ross and Goldberger and other collaborators. So the idea is that we can hide this ignorance about the time of flight, about the fact that we don't know if the wave left the system at some time in the bulk. We don't really know, can't really predict exactly when it will arrive at our large distance R, but we don't care, right? Because our experimental setup simply waits. The field is 0 for some time. At some point we see some field that fluctuates, and we can just fix experimentally this origin of retarded time. Say, for instance, the origin or the 0 of U by saying, for instance, that you fix it at the first peak. So I would say it represents a sort of conceptually subtle point, but from a practical standpoint, it doesn't really matter. What matters is that from this one, we are able to predict the wave shape from, so up to fixing its origin, literally the shape of the signal. And the other thing that I don't really have time to explain in detail, but let me just mention it, is that you remember earlier when we wrote down the form of the super translation, we said, the shear, which is just the AB part of this W, transforms, it has a piece that is T du plus other stuff. Okay, now the message is that if you go back and apply this formula, now keeping also the terms that are relevant for this order in G, you will find that it talks to this, in particular, it can modify the piece of these Compton cuts that I wrote over there, the ones associated to GM1 omega 1 times the log of omega 1 plus the same thing for omega 2. So shift GM1 omega 1 log of, say, omega 1 divided by omega plus same thing with 1 replaced by 2. So now it's important not only for the zero frequency part of the waveform, but also for the one that depends on time or depends on frequency when you write it down in frequency domain. Okay, thanks. I think that was all the material I had prepared. Thanks.